Hello, my name is Year Hess, and in this video I'll be talking about object detection as probabilistic set prediction. This is joint work done together with Christopher Peterson and Lennart Svensson. In this project, we have been concerned with probabilistic object detection. Over the last few years, it's been popular to describe object detection as a set prediction task, where models predict a set of objects in an image. Here, we view the set of objects as a stochastic variable and propose that models instead should predict a distribution over this set. One benefit of this is that we can optimize model predictions directly toward the true set of objects. Further, our method is compatible with existing probabilistic models, as we only need to reinterpret their predicted parameters. This reinterpretation, however, makes a big difference and improves detection performance as shown here. One way to motivate our approach is to look at how we typically solve tasks like classification and regression. For classification, we predict a class distribution to match the true class. For regression problems, we predict a density which should be close to the true value. In object detection, both types of problems are present. Previous work has predicted multiple distributions over class and bounding box, one for each object, and evaluated them individually. However, as there are multiple objects in a scene, the evaluation is dependent on how predictions are assigned to the ground truth objects. The importance of the assignment step has previously been overlooked. Instead, it has been treated as a separate problem to be solved with handcrafted rules. Wrongful assignments have then given a skewed picture of model performance. We propose a novel perspective for the probabilistic object detection problem. Specifically, we view the set of objects in an image as a single stochastic variable, a simple change which has multiple benefits. The task for the models then becomes to predict a distribution over sets, which best explains the observed set of objects in an image. This allows us to use standard tools like the negative log likelihood for evaluation. Further, we can use the same criteria for training and optimizing the detectors. In this work, we use a Poisson multi-Bernoulli random finite set for modeling the distribution over sets. Below, we visualize such a distribution and samples drawn from it. As expected, we see that realizations become sets of objects. For more details on this, we refer to our paper. The main benefits of using a PMB is that it is compatible with existing detectors. We only need to reinterpret their parameters. Further, random finite sets elegantly model the assignment problem. When evaluating the likelihood, we consider the assignments which have the highest likelihood. For our experiments, we trained 3 different detectors with our set-based loss and evaluated them with a negative log likelihood for a PMB random finite set. We found that, generally, our probabilistic modeling improves detection performance. Another advantage with the PMB negative log likelihood is that it can easily be decomposed into different types of errors, namely regression, classification, false positives, and false negatives. From these decompositions, we can see that training with our loss formulation, detectors produce fewer false positives and have better classification performance. These trends also become clear when doing a qualitative inspection of the detections. Detectors trained with previous methods tend to produce multiple detections per object, where each detection is a separate hypothesis. Looking at the ETR with energy score, the model has many guesses for the spatial extension of the surfboard. Our method instead results in one confident prediction per object. The detector is still uncertain about the surfboard size, but it is instead captured in one detection, which is more intuitive. These trends also hold true for the other detectors evaluated. To summarize, by using distributions over sets, we can accurately model the probabilistic object detection task. This helps us to formalize the evaluation and training objective and captures the assignment problem. Our method can be applied to existing detectors, and training them with our formulation improves the probabilistic object detection performance. Thank you for listening. Feel free to check out our GitHub page for more code and more information.